Hello everyone. In this video, we're going to be solving a differential equation in 3 different ways. And as I said earlier, the first method is just going to be a little bit painful. So bear with me while I go through all these methods. So we have this very simple looking differential equation, y double prime equals y prime. So y double prime is the second derivative, which is the derivative of the first derivative. And we have the first derivative on the right-hand side. We don't have a y in this equation. We only have their derivatives. Okay, so how do we solve this equation in 3 different ways? Let's go ahead and talk about that. My first method uses a power series. Yay! It's kind of like an overkill. I definitely know that. But I just wanted to introduce this because power series are very important in solving differential equations, and what could be better than a simple example to introduce the idea. Okay, so let's go ahead and define y as a power series, which is n equals 0 to infinity, a sub n, x to the power n. So this summation symbol is basically used for writing the following. If n is equal to 0, we get a sub 0, plus then if n equals 1, we get a sub 1x, and then a sub 2x squared, so on and so forth. And this goes on forever. Now, using this idea, we can basically just, differentiate this as a series and plug it into our original equation. So let's go ahead and do that. So from here, y prime is going to be, a0 is a sub 0. I just call a0 sometimes. A sub 0 is constant, so we're going to differentiate a sub 1 times x, which is a sub 1, and then we get 2a sub 2x, and then so on and so forth. So 3a sub 3x squared, dot, dot, dot. Now, we need to be able to write this, obviously, as a power series, like in summation, using the summation symbol. Here's what we can do. It starts, first of all, we have to realize n equals 0 is gone, so n equals 1 to infinity. And notice that we have the a sub n, but we also have the 2's and the 3's, which are the coefficients, so that's going to be n. And then a sub, now we have a sub n, and then that is multiplied by x to the power n minus 1. You can also get that by just differentiating this term, move the n to the front and reduce the power, so on and so forth. Same idea, but n must be changed. Okay, great. So n starts at 1 here. Now the second derivative is just going to be, this is differentiated one more time. This time it's going to be like 2a2, and then we have like 3 times 2. I want to write it as 3 times 2, and then a sub 3x, and then it's going to be like 4 times 3 times 2, a sub 4, x to the second power, so on and so forth. And this can be written with the summation symbol as the following. So if you're going to move the n minus 1 to the front, and of course n must start at 2, because we have a sub 2 as our first term, n equals 2 to infinity, n times n minus 1, and then we get a sub n, and this time x must be raised to the power n minus 2, because we lost 2 of the x's. Okay, great. So I got this one. Let's see what we have so far. This is y double prime, and I have y prime. Okay, great. So I'm going to use the summation symbols for now because easier. So this is y prime and this is y double prime. So let's go ahead and put them together because they're equal. So we can now set them equal to each other, and 2 to infinity, n times n minus 1 times a sub n, x to the power n minus 2 is equal to n equals 1 to infinity, n times a sub n, x to the power n minus 1. Now, obviously, you do want to set them equal to each other, but you also want to put them on the same side. So we're going to subtract. And when we subtract, I want to make the powers of x equal, because that's the only way we can factor and kind of leave the x outside and deal with the coefficients. Because you don't really want to deal with x. We don't care about x. Obviously, we just want to focus on the n and a sub n values. Anyways, so let's go ahead and do the following. I want to replace n with n plus 1 here. And if I do that, basically that's going to give me n plus 1 equals 2, which means n equals 1. So that's going to start our first thing at 1 as well. So that's kind of important because we're gonna be able to put them together basically if n starts at 1. Okay, I hope that makes sense. So it's gonna be n equals 1 through infinity, and now we have we're replacing n with n plus 1, so we get n times n plus 1, and remember this becomes a sub n plus 1, and then this becomes x to the power n minus 1, and then the other one is just gonna become, and I'm subtracting it, so let's go ahead and subtract them now, since they have the same n value, starting value, and that the second one is not going to change, so it's just going to be the same thing, n a sub n x to the power n minus 1. And this whole thing is equal to 0 because we're subtracting two things that are equal. Awesome. Now we can go ahead and do the following. Factor this out, like factor some terms, and those terms are going to be like this. We're going to have n times n plus 1 multiplied by a sub n plus 1 minus n times a sub n, and this whole thing is going to be multiplied by x to the power n minus 1 is equal to 0. So you kind of have like a bunch of a sum of powers of x, but that is 0. That can only happen if the coefficients, all the coefficients are 0. In this case, this basically represents all the coefficients. So let's go ahead and set that equal to 0 and see what happens. N times n plus 1 times a sub n plus 1 minus n sub a n equals 0. And we can go ahead and set these equal to each other. And we have to make an assumption here, which we can deal with separately. N should be different from 0 here, obviously, right? Because you want to get rid of the n value. So suppose n does not equal 0, we can get rid of this. And now write a sub n plus 1 as a sub n divided by n plus 1. Now this is a very important relationship we were trying to get for our differential equation. Now let's go ahead and see what it means. So for n equals 1, this means a sub 2 is going to be a sub 1 divided by 2. For n equals 2, this is going to be a sub 3 equals a sub 2 divided by 3. But since a sub 2 is equal to a sub 1 divided by 2, that is going to a sub 1 divided by 3 times 2. With n equals 3, you're going to get basically a sub, for a sub 4, you're going to get a sub 1 divided by 4 times 3 times 2. And obviously, these can be written as factorials. Yay! That's the fun part, because this is going to turn into something amazing at the end. So those are my coefficients. Let's go ahead and plug in everything into our equation, because now we have a series for y. So I get a sub 0 plus, remember, it was a sub 0, and then, the next term is just going to be a sub 1x, right? And then we're going to get a sub 2x squared, but instead of a sub 2, I can sub a sub 1 over 2 factorial times x squared, and then a sub 1 divided by 3 factorial x to the third power. I hope you get the idea. Now I'm going to do a little bit of, manipulation here, because I do need an additional a sub 1. So I'm going to subtract a sub 1 and add a sub 1, and this is going to be real cool. All right, so now bear with me while I work through this. And now this is going to turn into something amazing. And that thing is this one. So I'm going to call that something else, but look at this. Isn't that amazing? It's beautiful. So now let's go ahead and call this just a c, like a constant. And the rest is basically, if you take out an a sub 1, you get 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. And if you said this is e to the power x, you got it right. It is e to the power x, the Euler's number with all its glory. Awesome. This brings us to the end of the first method. Bear with me because this is going to be a long video. All right, let's talk about the second method. The second method, basically, obviously it's much shorter than this first one, is going to involve the following. I'm going to set these equal to each other, and I want to think about it this way. Okay, the second derivative is the derivative of the first derivative, right? So I can write it like this. We have two functions whose derivatives are equal, right? One of them is y, the other one is y prime. Amazing. So we can go ahead and put them on the same side like this. And the derivative of a difference is the difference of the derivatives, or something like that. So I can write it like this. Now think about it. The derivative of which function is equal to 0? And the answer is the constant function. Yay. So y prime minus 1, y prime minus y must be a constant. Let's call that c. You see what I see? Y prime becomes y plus c, And now I can write it as dy over dx with my infinitesimals, and they are infinitesimals. Some people said they're not. They are. So anyways, from here we get a really nice separable differential equation. Yay! So now we can solve it by integrating both sides, and this is what we get. And I'm just going to skip the, cases here like y plus c. I'm just going to assume that it's positive. If it's not, you can put a minus sign with the absolute value, so on and so forth. Let's just skip those, details and just assume that y plus c is always positive. And now when you integrate, it's going to be ln y plus c equals x plus k, k being just another constant. Let's go ahead and write this as e to the power ln y plus c equals e to the power x plus k with all the domain conserved, like ln is only defined for positive values, so on and so forth. And now we get e to the power x times e to the power k, but e to the power k is another constant. Let's call that m. And this gives us the following. E to the power ln y plus c is just y plus c equals m times e to the power x. We're almost there. Bear with me. One more step maybe. We can write y as m e to the power x minus c, and negative c we can just call that n. And this brings us to the end of the second method. Yay, we're almost done. So now notice that with the first method we got y equals a constant plus a1 times e to the power x, which is constant plus another constant times e to the power x. This is the same thing pretty much. Get the idea? Hopefully. Now here's the third method, which is going to be probably the coolest method. And this is a general method for solving differential equations. We can turn this into y double prime minus y prime is equal to 0. And then we can use our differential operator. D squared represents the differentiating twice, and d represent differentiating once. And we can write our equation like this. And d is the differential operator. And from here we can write the characteristic equation, which is r squared minus r equals 0. And this is factorable. R times r minus 1 is equal to 0, which means r equals 0 or r equals 1. But with the characteristic equation and its roots, we can basically write the following. Y equals, if the roots are r1 and r2, basically solution is going to be like c1 e to the power r1x plus c2 e to the power r2x. Since our solutions are 0 and 1, 0x is just going to be 0 and e to the power 0 is going to be 1. Therefore, you're going to get something like c1 plus c2 e to the power x as before. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know what you think. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.